Hello everybody, here in this video we will learn about time series, what exactly the time series analysis is, right? So what exactly time series analysis is. So in this, in short, I can say in this, using the date time variable, we try to predict the dependent variables. Dependent variable could be anything like amount of sales, price of stock, or anything. So usually what happens is in this data, for the time series analysis, what we actually get is two kind of variables. One is independent, which generally the date time column is this here. In our case, this is the one. Now there will be one dependent variable. In our case, that variable is passengers. This data is about air passengers, okay, where you have the information for number of passengers for a specific airline, month on month, growing or decreasing. Okay, now using this data in this exercise, we will use the same data and we will try to predict the number of passengers on a certain point of time. So this is it in a nutshell. This is what exactly we learn, or this is exactly what for which we use the time series. Okay, what are the other examples, if other applications for time series, if you ask me, then we can say that we can use this for sales forecasting, we can use this to predict the temperature, weather, or whatever it is. Okay, we can use this to predict the price of our favorite stock, and so on, right? These are the images which I have taken from Google. All right, so these are some of the applications or uses of time series analysis. In this series of video, we will be understanding what exactly the time series analysis is, what are the models that we can build on time series analysis, in time series analysis, and many more. Let me take you to the Jupyter notebook and try to help you understand with practical examples. So here, before we start, these are the prerequisites which I have already imported. I expect that I believe that you are already familiar with all these libraries. Okay, if not, let me know in the comment section. I'll help you with each of these libraries, and or if you want, you can find the videos, tutorials for each of these libraries which are available on this channel. Okay, now moving forward, let's try to have a look on the data. How to get the data in Seaborn library. Seaborn library also provide list of data sets. Okay, so how can we see what are the lists of data sets? For that, what you can do is you can say sns.get dataset names and call this. Okay, so this is what you get. This all are the data sets which are available into this Seaborn. Okay, now we will be taking this flights data. This is the air passenger data which I was showing you in the very first. Now let's just try to import this. How would you import this? For that, you're gonna say, don't worry, you don't have to use pandas because you're not going to import that from Excel. It is already available in Seaborn. We just need to load that. So here we're gonna say sns.load data set, and in that you just put the data frame name, and let's just see, we will put it in a data frame, and let's try to see a sample of this data frame. Okay, like you can see, this is how our data set looks like. Here we have year column, month column, and passenger column. So we need to convert it into one complete date, but the problem is here we have only year and month, so we require a day part also. So here what we will do is we will take one common date. For example, we will take first day of each of the month, because last day for each of the month will be different. So here we will take first day of each of the month, and we will try to combine them all together, all these three together, and then we will have one date column. So let me give a name to that. Let me create a variable called year month, and into that I'm going to concatenate or combine all these three things. So first thing which I need is day part dash plus, here I want to use year column, but the problem over here is this is integer variable. Okay, so we need to convert that into string and then concatenate. How can we do that? So for that, simple, you just need to put the variable name and then just say as type. Into that you can just say str. Okay, this is it. Then after that you need to put a dash. I will be putting a dash. Then the next thing, I will again repeat this same thing, for month column. Now you might have a question that month column looks like text, but this is not true. That's the categorical variable, okay, that we also need to convert it into the string, and then we need to sorry, use that. Now if you see, this is what we get. Now like you can see over here, okay, let me do it differently, and over here I will call it year. Now this looks much better. All right, so this is how but the problem over here is this particular column which we have just created is not the date time column, okay, it's not the date variable. So in that scenario we might have trouble, we might struggle handling this variable or doing the analysis. So what I'll do is I'll just use one function. Let me call that pd dot to date time, and let me just put all these things inside that. Now we have this in date time format, and if you want to have a view on the sample data, this is how this looks like. Okay, now what I need to do is I'll be converting this particular column into index. Okay, I'll make it index so that it will be easy for us to handle this. Okay, if you want you can continue in the same way, but here for the convenience I am just doing this df.setIndex, and you just supply the column which you want to use as index. Now let's just see, this is how our data looks like. Let me just call it df.head. Oops, here you need to say in place equals to true, in place equals to true. All right, now here you see we got this data. Now let's try to plot this data on a line chart. Okay, how can we do that? Let's say sns.line plot. I've created a separate series for on Seaborn and on Matplot also. So if you're someone who is new to visualization in Python, I highly recommend you to check that out. Okay, so sns.line plot, and here in the data frame, okay, in data argument or parameter I'll just supply the data frame name, and then on x-axis I want to use df.index. okay, df.index, I will use this particular column. Okay, see how simple it is. Now what next? On y column I will be using df.passengers. all right, now let's just plot this. So you see this kind of graph we are getting. When you observe this particular graph, what we see is it shows us a trend. Why it is called trend? Because if you I mean there is one word which you got, okay, which is trend. What does that exactly mean? Other than trend, you also see up down up down up down by a specific time. That's something which we call as seasonality. We can say seasonality, right? What all these key terms are, these are nothing but the patterns. So in time series usually whatever patterns that we get, usually those are classified in 4 categories. Okay, what are those 4 categories? Let me take you over here and try to help you understand. So those 4 categories are trend, which we just saw, then seasonal, this was also combined with the trend, then cyclic, and then irregularities. Okay, let's try to understand one by one. Trend is something in the data. When you plot the data, you will see either the dependent variable is growing or it is decreasing by the time. So you see over here this variable is growing, it's increasing by the time in accordance with as you grow by the x-axis, it is growing upward. Here it is downward. Okay, by x-axis as the time grows, this particular dependent variable is decreasing. Okay, so this is kind of trend pattern. We also called it component of time series analysis. Okay, this is the trend one. Next comes the seasonal one. For example, have a look on this particular chart. What you observe is this. Before I explain you, let me tell you, this is, let's consider this is a completely hypothetical data for ice cream sales. So if you observe over here, the sales of ice cream starts to increase by the beginning or before beginning of April month, and it keeps on growing, and then it starts falling near to October, and then it keeps on the lower level till again at the beginning of April. Then again it is coming down, it goes up and then comes down at the start of October and so on, right? So what you observe is from April till October, starting from beginning of the April till starting of October, this is growing. Okay, this is growing. So what you see is by the time, if you see, there is a fixed pattern. So in India usually we have summer season during this time. So what we observe is during the summer the sales of ice cream is increasing, and you see summer is season, so during this time frame the sales is increasing. So whenever dependent variable either increase or goes down for a specific time period, right, and that repeats and that gets repeated on a fixed frequency, that's where we call it seasonality. So every year in the month of April to October, the sales of ice cream is increasing and then it's falling. That's why we call it seasonal. I hope that it is clear to you. Next comes cyclic. Cyclic is something which starts and then continued for some time, keeps continue for some time, and then it goes away. And then there is no fixed time when it will come again, right? It could be positive or it could be negative also. In terms of negative, if you take example of recession, COVID, so what happens is you get this kind of trend, right? This kind of trend. For example, if you take a recession, so there have been multiple times when recession came, right? So it will come and then it will remain for some time and then it will go away, then everything will remain smooth. Then again at certain point, I hope that it never comes, but it may come, right? Again, then that will go and it will remain for some time, and then again the things will come up, right? Same thing happened in the COVID also. So those kind of things called cyclic. Usually this happens, in case of depression, recession, and all those things. Okay, then comes irregularities. So in case of irregularities, you don't find any kind of pattern into it, right? You don't see any pattern in the data. We also call it noise in the data, and we try to avoid this. In this case, it becomes really difficult to do the analysis. By now we have understood the component or patterns which we generally find in time series, and over here on this graph we can clearly see that there are two patterns into it. One is seasonality and then the other one is trend. Okay, so if you just start building model on this particular data, that might turn out to be biased, or maybe some sort of overfitting and something like that. Okay, means the model may not turn out to be accurate, because why? Here the data is clearly showing as the time passes the number of passengers will increase no matter what, right? So the model will not give the correct output, may not give the correct output. Okay, so how to fix this kind of thing? So before start to build the time series model, we check out the suitability of the data. How do we check the suitability of the data? So for that we figure out stationarity, right? How stationary whether the data is stationary or not. Now you got a new keyword, which is stationarity. What does stationarity mean? Let's understand that, and then we will understand how to figure out whether the data is stationary or not. So stationarity means, simply, if I put it in very simple layman term, then it simply says, I wouldn't say clearly or what, it simply says that mean and variance or covariance or standard deviation of the dependent variable don't vary by the time. What does that mean? Let's say that if we plot our data on this x and y axis, and if we are getting this, the data is completely hypothetical, and if we get this kind of data, this is stationary. Why? Because you see this mean, it is traveling alongside the x axis, which remains, it's a straight line you are getting for the mean. So that means the mean is remaining constant by the time. X axis represents the time and y is representing the dependent variable, whatever it is. And now if you see the variance, that is also traveling alongside the mean or x-axis. So here we clearly see that the data is stationary. Now let me show you some more examples. Here I have taken some of the images which I have directly taken from the Google. This was very much suitable to explain it. Okay, so the credit goes to Google itself. Now here you see this is same as what we just saw, right? Here you see stationary mean and stationary variance. Means here mean and variance both are stationary, means both of these two things are constant, that is not changing by the time. Okay, if you see the line is straight, so mean of this dependent variable remains approximately same and variance also remains same. Now let's have a look on the different image. What you see over here is the line in the center represents to mean and this two blue line represents to the variance. So mean is not constant. If you see, it is first, it is trending, it is showing you a trending pattern. First it is increasing and then it is falling. Okay, you can also consider it as a cyclical. Okay, but what you see is variance that remains constant. This increasing and falling line doesn't show that variance is not constant. This is alongside the mean, where you see the variance is constant. Okay, variance is constant but the mean is not. Now let's have, if it is confusing, let's have a look on another image. Here what you see is mean is constant, that means mean is stationary, but the variance, the top and bottom line are not constant. You see initially it is more, then it is reducing. Okay, so that means the variance is not stationary. If we put all these three images together, this is what we see. The first one is stationary, where mean and variance, both of these two things are traveling alongside the x-axis. That means both of these two things remain constant by the time. In the second one, what we see is the mean is non-constant, but the variance remains constant. So that means this is also not stationary. This one is also not stationary. By now I hope that it is clear to you what stationarity is. In case if you have confusion, put that into the comment section. I'll explain it in a separate video. Moving forward, how to check the stationarity of data, how to specify, how to validate whether our data is stationary or not. Though by simply looking at the graph, when you plot the graph, and if you are able to, there are 4 patterns which we learned in the previous video. Those 4 patterns we find in the time series, right? So if you see trending and cyclical, trend or cyclical were trend, cyclical and seasonality, these were the components or pattern in time series. So if you see, if the plot is either trending or it's seasonal, then that means it's stationary. But still, if you want to specify that more particularly, how do you do that? So for that, there are mostly these 2 ways are used. Number 1 is ADF. What is ADF? Sometimes it is also called ADCF. Not sometimes, somewhere it is, you would find that it is also used as ADCF, but the meaning remains same, which is augmented decoupleur test. Now there is a Wikipedia page for this. You can check that out to have the detailed understanding. I'll provide the link in the description section. And this augmented decoupleur test, in this what we do is we completely deny whatever the data is. We completely say that the data is not stationary. That's the null hypothesis we will take, and then we will do this test which will specify, or this ADF or ADCF test either will reject or accept the null hypothesis, right? So in beginning we will set our mind that the data is not stationary, and then we will do this test to specify whether the null hypothesis can be rejected or accepted. Then what is the output? How do we specify this? So out of this test we get these 2 values, test statistics and critical values. So if you get, there are other values also which we get, but primarily if you see if test statistics is less than critical values, you can clearly say that the data is not stationary. Okay, I'm sorry, here I made a mistake. I should have to say if test statistics is less than critical values, then we can say the data is stationary. If it is not, then the data is not stationary. So basis on this, we can either accept or reject the null hypothesis. Okay, the second test is which we can perform is rolling statistics. In this, we simply take the rolling mean or rolling variance or standard deviation and we will plot that, and this is the simplest one and provides the best clarity, okay, by visualization. All right, so now lots of talk, let's go to the Jupyter notebook and try to do this. Okay, so first let's start with performing the rolling statistics. What we can do is let's try to create a variable in our data frame. Let's call it roll mean, and into that what we're gonna say is df dot passengers dot rolling, and here you need to specify a window. What does window means? Window means by how many months or by what time frame you want to roll the average. Now if you want to understand rolling mean or rolling statistics, there is a separate video which I have created, link I am giving in the description section. You can just check that out. If that clarifies, it is okay. If not, let me know into the comment section. I'll make a separate video. So here I want to roll the average by 12 months. Okay, so I'll simply say 12, and because here I'm going to create the mean, so I'll just say mean. This is the simplest way of doing this. Now there is another variable for standard deviation that I will create, and I will say STD, and here I will just change it to STD. All right, we are done. Simple. Now let's try to plot this. Okay, so the first data set which we are going to plot is line plot, and into this data equals to TF, where on x-axis I'm going to plot the, on x-axis I will plot index, because index is the column which has time, right? You see over here. Then the second one, on y-axis I'm going to plot passengers. On y-axis I will just say df dot passengers. All right, we are done. So here it is exactly same what we got previously. Now let me specify the image size also, plt dot figure, and into that you can just say figure fix size, and just let's just give the dimension so that it will look little better. Now let's plot the mean also. Here I will just say, here I would say roll mean, this variable. Okay, now the next one I'm going to plot is standard deviation, STD. Sorry, this should be STD. No, it should be roll STD. Roll STD. This is all right. So we are done over here. Now here what you see, if you remember from the previous example, here you see this line represents to the rolling mean, this orange line represents to the rolling mean, this green line represents to the standard deviation. Okay, rolling standard deviation. So what we see is standard deviation is approximately, you know, stationary. That means it is approximately constant to the timeline, right? But if you see the mean, that is not stationary. That means it is not constant, it is trending. Rolling mean is also showing the trend pattern. Okay, it is increasing by the time, which means our data is not stationary. Now let's try to perform the second test, which is nothing but the ADF test. Okay, which I just explained over here, augmented Dickey-Fuller test. Okay, augmented Dickey-Fuller test. Now let's see how can we do that. So for that you need to import a module from statistical, I would say stats models dot tsa dot stat tools import adf Dickey-Fuller. Okay, now we got it. Now let's create a data frame called ADF test, and over here I'm just going to put Dickey-Fuller, and inside that I will take the variable which is nothing but passengers. If I can copy this, yes, it will be quick. So here I put this, and there is one more parameter which you need to pass on, and that is this one, auto lag equals to AIC. This is default one which you need to pass over here. No need to put much mind into it. Now this is done. Let's try to see what is the value that we are getting. All right, so we got this value, but it is not clear what does it represents to. Let me make it clear. Right, so there are two segments you can see, this one and this one. So this is criticality and this is the statistics, like test statistics, p-value and all those things. So here I have noted it all down, which will just put it, I'll just take it, I'll just take this. Okay, so for first of all, let me show you something. Okay, so if you say this and if you slice this 0 to 4, so this is what you are getting, right? The first segment. Okay, now what are these values? How would you know what are these values? Okay, so for that I'm just going to convert it into a series so that it will be easy for us. Okay, so let's just say stats equals to this, and here I would say PD dot series, and inside that I'm just going to say index whatever I have copied over here, right? I'll just put it, and let's just print that stats. You see over here, the test statistics which we are getting is 0.81, right? Now let's see the criticality. These are the criticalities. Okay, so we just have to print that. So for X, you see this is a dictionary. If you want to understand how to iterate through the dictionary, I have a separate video, just check that out. Okay, for key and values in we can say AD test filler, ADF test which we have created, and into that we want to pick the fourth element, dot items. All right, now let's just try to print key and values. But this is again, the story again remains same. So here I'm just going to say this, and here I'm just going to say this. I'm just trying to decorate it, nothing else. Okay, so criticality T. All right, now you see, so criticality 1%, 5% and 10%. This is the interval. So for 1% we are getting -3, -2 and -2. Okay, but see, the condition says over here that test statistics should be less than critical values, but the critical values which we are getting, that is less than test statistics, which means clearly our data is not stationary, right? So they hope this was clear to you. Now in the next video we will understand how to make this data stationary. What are the ways to make it stationary? Okay, I just hope that in this video we covered what stationarity is, what are the types of the stationarity. Okay, so types of stationarity, it is nothing but let's say it could be seasonal stationarity, it could be trend stationarity and all those things. And we also covered how to check the stationarity in the data. Hope it was clear to you. Are going to understand how to make the data stationary if it is not. Primarily there are three ways which you can use to make your data stationary. The most simplest one. Alright, before I take you to that, one more thing. Here is a quick view. So this is what we had understood in the previous video, where we tried to check the stationarity of data by two ways. Number one, this I'm just showing you because just in case if you have not seen the previous video, then you will have some idea, right? So we just discussed there are two ways of finding this thing, checking out the stationarity of the data. Number one, by rolling statistics, which we did over here, where we find rolling mean and rolling standard deviation. We plotted them all over here, and then we saw whether the data is stationary or not. In this segment we try to do the ADF test, or somebody also call it, or I mean somewhere it is also called as ADCF test, right? Basis on that we get certain statistics and which helps us conclude whether the data is stationary or not. Now coming back over here, there are three primary ways which you can use to make your data stationary. Number one, timesheet. This is the simplest one. Then log, then finding a square root, cube, etc. So these are the three ways. Rather, I can say whatever the ways are there, these are the most commonly used, right? And there isn't any fixed sequence that first you should go for time shift, then log, then square root and cube, right? You can try any of them in whatever sequence you want, but the most convenient way is to go first with time shift because that's the simplest one. Then it is also not necessary that you try all these three. If you find your data stationary enough on time shift itself, you can go ahead and start building your model. If you find it on log, then you can start with model building. Same goes with square root and cube. If you still don't find your data stationary enough or satisfactory enough, you can combine them also to find a satisfactory outcome. Let's have a look on time shift, what exactly happens over here. So let's say this is your data. If you remember in the first video, we saw this. So here you exactly shift the values by a specific interval. So if you notice over here we are shifting the data by 1 month. How? If you see the number of passengers 112, the data has in the month of January 1949, which is shifted to the February 1949. This is the shift which we have done. After doing this, same goes for 118. It was for February, but that is shifted to March, right? In SAS we call it lag. Okay, and over here we are saying it's shift. So here I am shifting the data by 1 month. If you want, you can shift it by 6 months, 12 months, 24 months, whatever the way you want. It's not necessary that you go by 6 12 only. You can also shift it by 7 months, 8 months, whatever fits well to your data. Then after shifting this, we find the difference of both of these two, the actual one and the shifted one, and whatever value we get, basis on that you can do your stationary test. How does it looks like? And then you can decide to go ahead and build the model. Same happens with log. In logs, what we do is we simply find the log of dependent variable, and then again we do the stationary test. If it looks fine, we can go ahead and build. The same goes for finding the square root, cube, etc. You simply find the square root, or in the similar fashion you can also find the cube. Here I have just shown for square root, and then you can see if this does not work. See, what you can do is you can also find the difference, and then you can do that. Instead of using the passengers, you can instead of using this actual value, you can try to use the log value of this and then square root that, and then find the difference and check out the stationarity. So there are multiple ways. All right, a lot of discussion. Let's jump to the Jupyter notebook and try to understand it with practical example. The moment you feel confused, just pause the video, put your doubt in the comment section. I'll be happy to help you. Here is what we did in the previous video. Before we move forward, what I'll do is, because we will have to keep on doing this test again and again, so what I'll do is I'll quickly make a I'll quickly put them all together and make a function, and then we will move forward with making the data stationary. That will be helpful. So while I make the function, enjoy. Exactly I did is, first I am trying to, whatever data you supply and whatever the variable you supply, for which you want to check the stationarity. This function I'm creating because we will have to keep on checking the stationarity again and again. All right, so for that reason this this function we have. Okay, so here first I'm trying to create the rolling mean, then rolling standard deviation, right? And once that is created, here I'm trying to do the ADF test, right? ADF test, and then whatever the test comes over here, I'm trying to print over here, right? One print is over here. This will do the statistics printing, and the printing, and then this is going to do the criticality printing. Okay, and this part is going to plot the data. Okay, let's test this if this is working well or not. To test that, here we have our data called df, and let's see, this is how our data looks like. Okay, we have AirDF also, AirDF, which actually should be the same data here. No, all right, no problem. So let's say df dot head. Okay, now we want to test this. So for that, what we can do is test the stationarity, and in that supply the data frame name, and then supply the variable name. Variable name is passengers, on which we want to do this test. Remember, this has to be in quotations. Now once you do this, this is what you get. All right, so this is how we will keep on using. So here you see, this is the actual value, this is rolling mean, and this is the standard deviation, and here you have the statistics. Well done. So we will keep on using this function again and again. Okay, so now before we move forward, let's make the data clean so that we could it would be easy specifically for us to continue our practice. Okay, so if you see in the data here, you have a lot of variables. So we are going to, let's create another data frame, let's call it AirDF, and in that I'm going to say df, and out of that I will just take passengers. This is all that I need. Okay, AirDF dot head, you see. Now that's all that I need. Okay, now let's try the first method. First method we discuss is by shifting the time shift. Now let's just try. So how can we do that? So here I have my data frame which is called AirDF, and in that I'm just going to create a variable called shift, right? And you can also say shift 1. Okay, or let's call it shift only, because we will keep on changing this and trying this. Okay, so this is what our shift is. Now after that, what you can do is you say data frame name dot the variable name to which you want to shift, and then say call this function which is called shift, and by how many months if you want to, do you want to shift it. So if you want to shift it by just 1 month, you don't need to put any value over here. Okay, if you want to shift it by more than 1 month, then you need to put the value. For example, if you want to shift it by 4 months, then just put it 4. Let's try with the simple one. So here we have AirDF, and dot here we are going to say this thing, like you can see over here, right? So here the value is shifted. Now the next step is finding the difference, right? So let me just create another variable which I would say, look, I'm trying to keep it to the absolute beginner label, right? But if you find it little annoying, so just try to watch it in double speed or maybe 1.5. Now the next thing which we're gonna do over here is this. We will subtract AirDF dot passengers minus this thing. Okay, now let's just see how the data looks like. Okay, so this is done. Now the next thing is testing the data, or let's just try if this looks much better. No, it's the same thing. Okay, so this is looking same. Now the next thing which we're gonna do is check out whether check out the stationarity of this data. Okay, so test stationarity, and the data frame which we have created is AirDF, and in that what we are going to use is shift difference. This is the variable which we will be using. Okay, so let's just call it over here AirDF. This is the data frame name, and the variable which we want to use is this. Now just hit enter and see the magic. Ooh, it showed the error Let me just figure out what the error is. Xorg contains information or NANs. Okay, so what you see over here is this NAN that is creating problem, so that's not an issue. Let's call it drop NA, and let's just do this and let's see if it worked. Yeah, so here is what we have. Now you see this is still much better, right, from as compared to the original data. Or originally we had the data like this, right, and after doing the shift transformation, this is how the data looks like. So this was the shift transformation. Next comes is log transformation, right? So let's just try to see how we can do that. So if you have not understood it pretty well, so before I move forward, let me give you a quick view. So if you see over here, test statistics is minus 2.65, while the criticality is minus 3.4 for first percent interval, and you see this is somewhere closer to this criticality, right, and p-value is 0.08. over here you see mean is fairly looking constant, but the variance or standard deviation is showing a kind of trend pattern. Okay, so this was the one test. Now let's move forward and do the another test. Before we move forward, let me just create a subset of the data again, and here I would just say passengers. Okay, let me just do a quick copy paste passengers, because I just don't want to waste the time. Your time is pretty much important. And let's just see if this looks good enough. Log df dot head. Yes, now here we have the data. Next step which we're gonna have is find the log of this value. Okay, for that what you can do is you can just simply say log, and inside that you just supply the variable which is log df, and out of that you can just take passengers, right, and let's see log underscore df. How does it looks like? So here is what we got. Okay, now there are two things. Number one, you can directly check the stationarity on this log variable. Number two, you can combine the above shifting method into this and then find the difference with log, not with passenger, and then you try to check the stationarity. I'll go ahead with the simplest one first, and then we will see if we require to combine it. Let's check the test stationarity. Okay, in this the data frame name which I want to use is log df, and the variable which I need to use is not passengers but the log. Okay, do I have no, I didn't get the error this time because we didn't use the shift thing. Okay, all right, this looks good. The variation is, you know, the variance is pretty constant, but original data and this mean is still showing the pattern into it, right? But just looking at the graph, we cannot conclude it pretty well. So let's have a look at the statistics. So in statistics, if you see this minus 1.7, this is fairly, you know, good compared to the previous one, and if you see the p-value is 0.42, and what is the p-value that we have in the previous one? 0.08. so still this one time shift looks much better compared to this log thing, right? So, and if you see, this is the mean curve and this is the standard deviation curve. All right, so this is what we had for this one. Now let me just keep this one is for here. I have an Excel and I'll put all the things over here. Let me just say shift wala part is here, and this is going to be the log, so that it will be just simple for us to quickly have a comparative view. Okay, let me just do this. Okay, now if you see, log is showing you the greater p-value compared to the shift one. Okay, now let's move forward and try to do the square root. For square root, again, what I'll do is I'll create another subset of the data. If you want, you can keep on using the same data, but just for simplicity, I'm going to use this over here. Oops, sorry. Here I have to use passenger. Again, I need to copy this. And here what I'll do is I'll just put it over here. All right, let's have a quick look on this square root df. And how does this look like? All right, so this is looking like a series. Now let me make it data frame. Okay, now here we have it fairly enough. Let's create another variable into it, and I would say into this sqrt square root and np dot sqrt. Inside that, let's just apply this variable which is df and this passengers. And now you just go ahead and have a look on this. Perfect. Now let's try to plot this. Now let's just try to check the stationarity on this data. Test stationarity. Into this, supply this data. The data frame name is sqrt df, and the variable which we want to use is sqrt. Let's just run this and see how does it looks like. Oh, this is terrible. Not much better, huh? Let's have a look at the p-value, that is 0.9, and then test statistics is negative 0.34. Let's just take this. By looking at the graph, it is looking terrible. This was the square root method. Here we got that also. Now the next thing which we can try is cube root. Still the shift thing is looking better. This has p-value of 0.08 and here it is 0.9. All right, let's move ahead and try the next one. Next one we gonna have is, let's take cube root underscore df, and here I will again take df subset passengers. Df subset passengers, and let's just have a look at it. And this is how our data looks like. Now let's create the variable. In this we will say cube root equals to df, and into this I just need to put this in np.cuberoot. np is nothing but numpy library. Okay, all right, here I got some problem, and the problem is right here. Instead I should use this as the data frame. Now we got it right. Here is what we have. This is cube root. Okay, now after finding the cube root, the next thing which comes is testing the stationarity. All right, now let's just go ahead and test the stationarity. The data frame name we are going to use is cube root underscore df, and the variable which we will be using is this. Now let's just see how our data looks like. Now this is what we get over here. By looking at the graph, it is not looking much different, but let's just see how is it looking over here. All right, so if you see, it has 0.8. Still the shift one is giving you the better result, isn't it? Shift method is giving you 0.08 p-value, and test statistics also fairly close to it. Now let's just try to combine log and square root both. So what I'll do is, first I have the log underscore df dot head. Here is what we have. Now let me make a subset and let's call it log df2, log underscore df2 equals to log df, and out of that I will just take the passengers and the log variable. and let me show you the sample data. This is how our data looks like. Now we have to perform the square root on log variable. Okay, so let's just say log underscore df2 log square root. Okay, and now over here let's call it np dot square root. Inside that, what we're gonna do is np dot square root, and inside that I will use log df, out of which I will take the log. So here we are just trying to find the square root of this log data. Now the next thing what you can do is you can find the difference of these two, and then we can check the stationarity on top of that. Or maybe let's just try to figure out the stationarity on this variable itself. Okay, because we have already combined two things, right? So let's just see how does it looks like. Test stationarity, and inside that I'm just going to put this particular data, which is nothing but log df2. Sorry, log df2, and over here the variable which I will be using is this. Let's just see how does it looks like now. Okay, and what is the p-value? Here we just combined log and square root. Okay, so p-value it is giving us of 0.3, which is still showing that shift method is doing better, right? If you go by this this test statistics. Okay, and the test statistics also, you know, somewhere I mean, we can say it's close to this criticalities, but p-value you see still shift one is much better. Now what you can do over here is, next thing you can try to, you know, shift this particular value. Let's just try this. Okay, over here what I'll do is log df2, and let's call it log shift div, log shift div, and over here we will say log square root. We are combining multiple things, so let's just see how does it looks like. Shift by 1. Okay, now this is how the data is looking like. This is shifted. Let's see how does it behaves over here. And we would have two variables already created inside it, rolling mean and all those things. Let's just see what happens. Okay, it is saying something NaN problem. Okay, because this shift value, right? So here I would say drop Na, and this is this working? Oh, it's pretty good, isn't it? Now if you take this, all right, so here the test statistics is 3.07, which is fairly close to criticality 1%, and p-value is 0.02, and the p-value which we have for shift is 0.08. so this is doing much better, which is log plus square root, log and square root. We combined three things over here, right? A square root, and then we combined shift as well, right? So when we combined three things, we relatively got a much better result, right? So this is how you can try different ways, right? And then you will get you may get a very good result, and then using that you can move forward to, you know, build your model. Now to make the model, ARIMA is the best suited model for time series. To make the model, we can use either stationary data, the data which we transformed and made it stationary, or we can start with the original one. So I'm going to start with the original or base data. Once we see that how to develop the ARIMA model, then we can try to build the same model on stationary data or transformed data. Why is that so? Because if you build the ARIMA model on a transformed data, you'll have to again transform it back to the actual form, which will take some time. And just to avoid any kind of confusion, I'm going to start with the base data. So before we start, let's have a look on our original data. This is how our data is looking like, right? Now let me make a subset of it. Subset, I will say ARP data, ARP, let's call it ARP, okay? And then out of DF, I am just trying to passengers, I will do copy, and here I would say deep equals to true, so that my original data remains unchanged. So I'm done with creating this data frame. ARP.head. This is it. Now once I'm done with this, I will create two more variables into it, where I would differentiate by 1 and I would differentiate by 12 as well. Why by 12? Because in the beginning we saw that the data is having trend pattern as well as seasonality, right? And the seasonality is on 12 months. So if we do it on if we differentiate by 12, that will help in reducing the seasonality, okay? So that's why I will create both of those variables over here, and as and when needed we will use that, okay? Now here let's call it ARP difference 1, first difference, let's call it first diff, and for that I will use ARP dot passengers, and here I would just say diff. So in this you don't have to use the shift thing and minus thing, it does rest of the things automatically, okay? Now the next one which I'm going to create is diff 12 diff, let's call it, or maybe let's call it diff 12, and in this I will put 12, okay? Now here is what we got. Next we are going to start with building the ARIMA model. To build the ARIMA model, first we need to import this. So we're gonna say from stat models.tsa dot ARIMA model import ARIMA, okay? I'm done with importing this. So I will not import all the libraries at once. I'll import them as and when it is needed, so that you would have the context which library is needed for what purpose, okay? Now once I'm done with importing this, I'm going to build the model. So when you build the model, first thing which you need to provide is the data. And for data we require the train and test data, right? Train and test data. Before I reach to that point, let me just show you a version, okay? So over here I'm just going to use, let's for example, let's try to use this data, and after this what we need to use is, let's see all the parameters. So you see here you have to supply the data, then you have to supply the order. So for order, you see here it also says auto regressive integrated moving average. So this is the full form of your ARIMA model, and that takes PDQ as order. If you come over here for order, we require PDQ. Now let's try to understand what exactly this is, right? So for that I'll take you over here. Here if you see, ARIMA itself is a combination of 3 models. One is AR, then I, then MA. Let's understand each of them. AR stands for auto regressive and it is indicated by P. I stands for integrated and that is indicated by D. MA stands for moving average and that is indicated by Q. So this is how we call it ARIMA model. Now let's try to understand how to get the value, because here in the model you need to supply, you would require to supply the value for order. So the value which you would be supplying, that will be for P, D and Q. Now let's understand how to find its values. So to find the value, first let's start with D. D is nothing but integration. So what does it mean? You remember, this is how we have the data frame, and when we differentiate it, this is how we get, right? We just shift it by 1 and then we find the difference. So by how many steps we are shifting it? 1. So here the value for D will be 1. When you shift it for 12 months, the value for D will be 12. By whatever interval you shift the data, that will go in D. Next comes is autoregressive model. So to find AR value, we check the PACF. PACF is nothing but partial autocorrelation function. Okay. Then comes MA, moving average, which is indicated by Q, and to find that we use the ACF. Now I will not go in mathematics how to find this mathematically. To keep it simple and specific, I'll go and try to find it in Python itself. Okay. Now let's go back over here. So here we require the order values. For that, what we need to import is from stats models dot graphics dot some plots, plot tools, I guess, import plot, import graphics, then it should be ts plots, import plot ACF and plot PACF. Both of these two things I am importing. Alright, now once we are done with importing this, let's try to plot the data. So first we are going to build our ARIMA model in context of first diff, right? So here what I will do is I will use my data, let's call it ARP, and here the value which I am going to take is passengers. Not passengers exactly, it will be first diff. And because it has NA value, so I'm just going to say drop NA. Drop NA. I'm just waiting for it to complete, to do the autocomplete, otherwise it will just give you the error. And then it takes the value for lakhs. So I'm going to keep the value for lakhs is 20. If you want me to cover this thing in detail, let me know in the comment section. I'll try and cover that in detail, make a separate video for that. So here is what we got for PACF. So let's see how to find the PACF value. So you see this shaded area, that is insignificant area. Area outside of this shaded one, that is called the significant area. So the point where these lines are exceeding to this insignificant area, that is something which we're gonna consider, right? So this is 0. This is 1. At first it is exceeding, then here at downside also, here also it is exceeding. So we can try different combination of it. So first P value which I am going to take is, this is the value for P. Alright, PACF. So value for P I would have is, I would have value for P is 1. Okay, now let's try to find the value for Q, because for D we already have the value. So to find it, we're gonna say plot ACF and the same thing. Okay, rest of the things are going to be same. So here also it is saying the first one is out of the insignificant area, then second is nothing, then third. Right, so I can try with first or maybe third, right? First, second, third. I can take it third as well. Q equals to 3 and D value for D we already have as 1, right? Now this is the value which we got for PQ and D, or PDQ, right? Now next thing which we need to do is find the make a train test do a train test split, so that on train data we will train the model, and then on the test data we will test the model. Now let's start with making the train test split. So for that, the total length of data that I have is ARP, that is 144, which is for 12 years, because we have the monthly data, right? Now I'm going to split 70% for training and 30% for test. How is that going to work? You see over here, this is the same data which I have plotted. Now if you see, starting from here till here, right, that I will make as training data, and the point where it ends, starting from there till the end, I will keep it as test, right, for testing data. Now I just hope that it was clear. Now let's find the 70% of this data. So for that, what we're gonna do is length of the data frame into 70 divided by 100. Let's see what comes. It is coming 100, sorry, it is coming 100.28. Now we need to make it round, right? So this will be 101. Now the time comes when we should fetch the train data, train, and for that I'm going to say ARP starting from beginning till this point, right? That will go in train data. Let's just see how does it looks. Train dot head, right? So it is starting from this 112 and will go till the end. Let's see where does it ends. Till, so here it is ending at May 57. Now our test data should start from the month next to it, which is June 1957. Let's make that. Here I would say test data, and in this column I will pick this column from here, and I'll just put it here. Here it says start from this point where 70% is ending. From that point I want to start it, and here I will check test dot head. All right, so we are good over here, right? So here you see we are getting the June. Now let's just start. Now let's just start with actual model bending. Okay, now here I would use train data instead of original full data, and here we are taking the passengers. Please note, we are not to train the model, we are not taking this difference data. That is something which we just use to find the value for P, D and Q. Now for P, the value which we have is 1, for D we have it 1, and for Q we have it 3. Let's try to fit the model. Let's try to have the model object created. After that I'm going to fit the model. So to that I would say model dot fit. Model is fitted. Let's see if it gives any error. Looks good. Just ignore this warning, don't need to worry about it. Now I will make the prediction, and for that I would say model dot fit dot predict. Predict, and inside that I need to supply the data on which I want to make the prediction. So for that there are two parameters. We need to provide the start point. Start point will be test dot index 0. So we want to make the prediction on test data, right? And then we need to provide the end point, and for the end point I would use test dot index -1. Let's see if this gives any error or works well. Working well. Okay, now this is the prediction which is created. Now the next thing which comes is putting it in the data frame, which we have over here, right? The main data frame ARP. Okay, and then I'll try to plot that. So this is the prediction which is done. Let me just show you the prediction. How is that looking like? You see, these are the values. This is horrible. So ARIMA model is not working well on this. Okay, but anyway, just let's just put it in the data frame. All right, to put it in the data frame, what we're gonna do is, let's say ARP, and here I would create a variable. I would say ARIMA spread. Okay, and here I'm just going to say prediction. Let's just put the prediction and then see ARP dot head. Let's see. Okay, because of the NaN it is not showing you, and for that reason let me just say head 12. Okay, so this is the tail data, na? Test data, so that will be at the end. Let me say tail. All right, so here is what we got. Okay, now let's just try to plot this data. So SNS dot we had created it on top of train data, right? So let's call it SNS dot line plot, and here I'm just going to say train data equals to train x equals to train dot index and y equals to ARIMA spread. No. Let's just take this. This is your training data. Now because you build it on test data, so here I would say test, and here let's call it ARIMA. Okay. To build the model, to plot the graph, what we need to do is, let's take the original data frame, because in original data frame we have everything, right? And if you see, it has NA values. So what I will do is, I'll just drop them. Drop NA. Remember, this is not permanent drop. Okay. ARP. Now if you see ARP dot head, so it is going to, oops, sorry for the spelling mistake. Drop NA. So here I will say ARP dot drop NA, and if you say in place equals to true, that will be permanently removed, but at this point I don't want to do that. So for that, what I will do is, I'll keep it to this, right? Then I would say SNS dot line plot data equals to ARP x equals to ARP dot index, then y equals to ARIMA, this variable where we have stored our values. Now let's just see how does it looks like. This is how it is looking like, but it is hard to interpret how it is doing against the actual value. So for that, what I'm going to do is, instead of ARIMA spread, here I'm taking passengers. This is what our real value is, right? Now you see the difference. You see over here it is coming. So this is the reason, because ARIMA model is not fitting on it, right? So let's try to check the mean MSE. What is the error, right? So for that, I would say NP square root into this mean error. For that, you would require to import it first from sklearn dot metrics import mean squared root, mean squared error. Okay, this is the module which will help us to find it, mean squared error, and inside that I would put the value, these two values, right? ARIMA spread and the passengers. Okay, test data, let's say test passengers, and I guess that we have created this value, right? Now this is the mean squared error you are getting. Now if I do a square root for this, this is what we are getting, 427. So this is absolutely not a good model. Okay, so now the next step which we're gonna do is we're gonna see how to make it a seasonal ARIMA model. Okay, all right, now let's just start with building the ARIMA model. Okay, so how can we import? First we need to import that. So from stats models .tsa .ts space, or maybe it should be stat space .SARIMAX import ARIMA max. Okay, now this is done. Next thing which we need to, if you observe, there was one more variable which we had created, if you remember that was div12, right? Now is the time when we need to use this particular one. Again, we are going to find the ACF and PCF so that it will give us the value for this 12 difference, and then we will start with it. Okay, now first we need to find the value for PD and Q. Okay, now let's just do that, the value for PDQ. So first thing which we need to do is find the plot PACF, and in that the data which we need to supply is this, and into this we are just going to use this particular variable over here, say drop NA, and lags equals to 20. Let's just see. All right, in this, let me just do this. Okay, so here we don't have anything going significant, right? Going in significant area. So what we can do is, for ARIMA we can keep the value for PDQ same as we took it for ARIMA model, right? And here seasonality we can provide for 12 months. Let's start with this. Let's do that. ARIMAX, and here I will just say train data, and then here we need to provide train passengers. Okay, let me just copy it from here itself, whatever we had fitted. I'll just take it from here only, and I'll just put right over here just to save the time, and we will call it as ARIMA. Here it takes one more parameter, and that is called here there is one mistake. Instead of ARIMA we need to take ARIMAX. Okay, this is what we need to take over here. Now if you see the parameters which it is taking is, along with the order, it also requires the seasonal order, right? So let's just apply that as well over here. So in seasonal order, these three things, it comes PDQ. In seasonal order it takes PDQ, and over here it takes the seasonal number. Okay, so we have 12 month seasonality, so that's what I'm going to put over here. Okay, now this is done. It's not giving any error. Now let's just fit the model underscore fit, and over here we say model dot fit, and now the time comes when we have to make the prediction. And for that, again, what I'll do is I'll copy paste the things. Oops, sorry. Let me just copy paste it so that it will save time. Okay, now this is done. Next, in the data frame itself we will put this particular value, and I would say 12 months difference, div 12 months, or let's call it as ARIMAX spread. Okay, that was ARIMAX spread, and this is as ARIMAX spread. Okay, this is done. Let's just have a look at the data. p dot del, because that's where you're gonna get the actual view, right? Now here is what we have. This looks little better, right? Now let's just try to plot this. So to plot this again, I'm going to do the same thing. I would say air p dot drop na. This will drop the data. SNS dot line plot, and inside that data equals to air p, and from here I will just take passengers, or maybe if I can do a copy paste, or let it be just passengers, okay? And over here I can use air p dot index. Next on the y-axis I'm going to plot this as ARIMAX. Now how is that going to look like? Is it giving some error? Yes. What is the error that we have? Could not interpret value as ARIMAX spread. Why it is not able to interpret that as ARIMAX spread? It still says there is some problem. Okay, so here I don't have to keep it specific. Okay, I got the error, right? So this is our ARIMAX output. Looks pretty well because it also shows the seasonality. Now here instead of this I need to use passengers, and if you see over here, this is looking following the pattern. This looks like following the pattern. Now let's find the error over here. Here we already have the function, and let's just do this over here, and I will put this particular variable over here. Okay, again got the error, is not defined. Okay, I have to use prediction. So here we are getting error is 27, so which is pretty well compared to the previous one. Now this is done with as ARIMA, seasonal ARIMA model, which looks pretty well. Next thing, we need to find this thing for future data, right? How can we interpret this for future data, which we have not seen, which is not available. Before we move forward to predict it for the future, let me have a look over here. Here looks like I made a mistake. Here I should ideally use the 12-month differencing variable, this variable, right? I used a wrong variable over here to find the PACF, and so still we are not getting a bad result, right? So if you see over here, we have 1 and 2, both of these two are exceeding, and then 10th, 1, 2 and 10th. So if we can use combination of both of these two. So this is for p value, and for q we can find, for q what we can do is, let's make it ACF. Okay, all right, so this is looking pretty well, right? So here what we can do is 0, 1, 2, 3, 4. We can use all this combination to train our model in ARIMAX. Okay, so let's just start with, here I will for p I will take 2, and for d it will of course be 1, and for q also I would try with 2. Let's try 2, 1, 2. Okay, now let's just see how the data looks like. It's taking some time to train the model. Done. Then let's just see. It barely puts any difference, so we are good with that. Or maybe if you are thinking, we can try d equals to 12, and let's see what happens. Is there a change in the model? Ooh, this is terrific, right? So it can never be 12, right? So it will be 1. Let's keep that to 1. And then over here we can try this. Now let's try to combine the ARIMA pred as well, right? Let's try and combine ARIMA pred. I think this should, no, not ARIMAX, ARIMA parade. All right, so you see over here this ARIMA parade is looking, ARIMA parade is right over here, and this is how it is looking like. Right now to do the prediction for future, first thing which we require is to have the future dates, the data frame which we have that has the data for which we have already done the prediction. Now to do this for future, let's generate the data for future dates. Okay, so before that, let's just have a look at the last date in our data. So in our data, this is our data, and I will say tell into this, the last month which we have is December 1960. So we need to generate the date after December 1960. How do you generate the date for future? So for that, in pandas you have one function that is called pd.daterange. So you can use this. How can we do that? pd.daterange, let's call it pd.daterange, and into this you need to put the start date and end date. Start will be, let's say, we will just copy this and paste it so that it will be quick. Okay, let's just take this, and in this we will just change our values. So our values should be starting from January 1961. Let's make it, I will just try to copy this if I can. Yes, I can do this, and let's just put it over here. Let's just make it 1961. Okay, now I will make it for 24 month. Okay, let's just try for 24 month, and here let's make it 12, and this is 3rd. Let's just keep it till December. Okay, now at the end, if you don't give the next parameter which you need to give is frequency. If you don't give frequency, then it is going to give you the daily dates. Okay, but we require the monthly one. So for frequency, in here you have one frequency key which is called ms, that is month start frequency. Okay, because we have the starting date of each of the months. So here I'm going to say ms. Now let's just see how does it looks like. Okay, we got it. Now let's just try to convert it to pandas data frame, pd data frame, and here we go. Here we got it. Now let's just make it, let's call it dates. Okay, column name, oops, sorry, I need to say columns, and over here let's call it dates. Now we got this. Next thing which we need to do is I will just set it as index. Okay, to make it simple. Okay, first let's put it inside a data frame which is future date. Let's call it this future date, and then I would say dot set index. Inside that, the variable which I want to set as index is this, and in place equals to true. Now let's just see how does it looks like. Future date dot head. All right, so we are done with this. Now let's try to do the prediction on this. Okay, so for prediction we have our model created dot predict, and in this we need to provide the start, which will be start equals to, we can say future date dot index, and the 0th value, that is the start date, and then for end we're gonna say -1, and it says invalid syntax. Here is the problem. Now here we got our values predicted. Okay, this is the predicted value. Let's try to plot this dot plot. All right, so this is how it looks like. Now what I'll do is I'll store this value. Okay, let me take this from here and here we already have this created. Just along with this I am trying to put this, how does it looks like. All right, so here we got that. So you see the red line. Okay, if it is not looking pretty clear, so let me change the color equals to black. And now let's run this. So you see this is absolutely in sync, right? This is absolutely in sync. Till here our actual data ends. This orange line which you see, that is the prediction on test data, and this is the prediction on future. So this is how you can play around with the models. You can try different values for PDQ while training the model, and you can have a very good model. Alright, so this is it in this video. Moving forward, we will try to build the model on transform data, the data which we transform to make it stationary. We will try to use that and make the model on top of that. Let me know in case of any confusion. Try to put that into the comment section, and then we will see it further.